In BaseGame 4, we modified BaseGame 3 to include a render class. The render class, similar to the physics class, performs a common task for all game objects, drawing them to the screen. The render class's functions now carry the burden of drawing background objects and flipping the display. Basically, all the code that has anything to do with drawing should be in here. So we can replace the relevant code in game's draw function with our render functions. In BaseGame 2, we noticed that the physics classes had similar functions to allow working with multiple object types. This means we might end up having repeated code since animated object and enemy both get drawn through the identical process. Luckily, there's a way to avoid this. First, we looked at encapsulation, the process of keeping related code bundled together. Then we saw inheritance, the concept of extending existing code in a modular fashion. In this final installment of the Principles of Object-Oriented Programming, we bring you polymorphism. Polymorphism is the idea that each derived class may maintain the functionality or identity of its parent classes. Here's the simple, quintessential example for polymorphism. You'll hear this one everywhere. You have a class called animal and a function called move. Move takes an animal as a parameter. Animal has a class that's derived from it, mammal. Mammal, in turn, has a derived class called wolf. Move takes an animal, and since mammals are animals, and wolves are also animals, both may be used as arguments in that function. No matter how many levels of inheritance you have, if a class is at all based on animal, any function that takes an animal will take that class. So in the context of our program, if we have a class that takes a game object, then our enemy and animated object classes are both valid parameters for this function, since they're also both game objects. Remember though, this only works when the only members this function works with are base game object members. If any derived class members are needed, then that class must be the parameter. So in render's draw function, we only need to access x, y, and bitmap. So for our render class, it doesn't matter what type of game object we have. In the game class, we pass render a pointer to the object we want to draw, and the program will disregard any of the bells and whistles that come along with the derived class. For all intents and purposes, that object is a bog-standard game object. Again, this is only because all classes derived from GameObject are identifiable as game objects. In previous tutorials, we've written child classes that override base class functions in order to provide new functionality. For example, we can have an effect class that is extended by a child class called Edge. Edge overrides a base function called apply to allow new functionality. This is great because someone using any effect-derived class shouldn't have to care what kind of effect it is. They should be able to tell it to apply and let it do its thing. We created a few different effect-derived classes and implemented a different visual effect for each of them. Polymorphism allows programmers to decide which version of an overridden function to run. Derived classes always have access to base class versions of a given function. When a function that has been overridden is called, the program assumes that the overridden version is the one to execute. You can, however, cast or force the base version to be used instead. In this tutorial, we'll use the effect class together with render to draw objects with special effects. Critically, render's draw function will need a parameter that identifies the effect to use. The difficulty in the above design, at least, as far as effects are concerned, was that the render class needs to know all the effect classes in order to use the right one, despite the fact that the render code does the exact same thing for all effects. We could specify the effect type as a parameter, or we could make it a member of GameObject. Which method is better? Should the effect be something intrinsic to a game object, or something external, so that the same object can be drawn with different effects? In a game engine, the render class may be developed separate from effects, and the user may add new effects to the system. So the render class code should not depend on the effect classes. Ideally, the render class deals with effects the same way, regardless of what type, since it only needs to call apply for the effect to do its thing. The problem we have is that since we're passing render a generic effect object, when it applies the effect, it's going to use the generic base apply function because that's the only one it knows about. This is, of course, of no use to anyone. However, there's a way to have it use the appropriate child version instead of the base one. We do this by declaring the base function as virtual. A virtual function is a function that is expected to be overridden in the future. Whenever the function is called through the base class, the program always uses a derived version if one is available. This means we can pass in a generic effect class and it'll just work. The program will work out which version of the function needs to be run. In many cases, the base version of such a function isn't even needed, since we always intend the effect to be defined in the child. In this situation, you might want to consider using what's called a pure virtual function, or an abstract function. As the name implies, an abstract function is just conceptual. It isn't intended to be used at all, as derived classes will provide their own definitions. We define a pure virtual function by writing equals 0 at the end of the declaration. Any class that contains a pure virtual function is itself a pure virtual class, or an abstract class. This class is incomplete and exists only to serve as a basis for other classes, not to function as an independent object. We can still declare it as a parameter for a function though, since any actual instance of an abstract class is guaranteed to be a child class. You might recall way back when we first introduced the concept of object-oriented programming and classes, we divided members into private and public. Private class members are inaccessible to any code except the functions of that class. That means even the functions of a child class cannot access those members, even though the child class itself inherited them. In many cases, we don't actually want a member to be accessible to external code, but we do want it to be accessible to derived classes. In those cases, we specify the member as protected. In the GameObject class, we always want the bitmap to be valid, so we set it to private so it can only be changed by calling the setShape function. There, we'll check to make sure the bitmap is indeed valid. A function such as setShape is called an accessor function because it's the only way we can change the class's property. And because it's the only way to access the property, it's very secure. We don't want to run the risk of accidentally setting the bitmap to something impossible and breaking the program. The speed property should also be accessible through a setSpeed function, but it should be okay to allow child classes to directly access it for convenience. So speed can be set to protected. Position we don't care about as much, so we can set it to public. And that's it for Module 5. We'll meet again in Module 6.